Hey, what's up? It's your old pal, Mr. Cook, and we are going through these problems. Just went through a doozy. My gosh, 15. That took a little work, huh? So yeah, let me erase some of this, and then we'll start working on the limit comparison test problem with the P-series, and go from there. I don't know. I'll do a couple at least in this video, and then and probably take a break. I'll finish up the rest of the video like tomorrow morning. Okay, so 16. So we went through a video earlier that tells us how what to look for in each different method. Found that this is really close to just comparing it to n over n squared, and when you reduce it a little bit, it just turns into a p-series. So we're going to use limit comparison test to show that this thing is going to. Well, let's find out. If we use p-series on this, the p-value is equal to 1, and that means that this thing will diverge. So I'm going to claim that this is going to diverge too, and I'm going to show that through the limit comparison test. Okay, so first off, we just make a fraction. So we take the limit as n goes to infinity, and then we make some fraction out of this. And it doesn't matter if you choose to pick this sequence or this sequence to use for the top or the bottom. But I usually like to write it up and then see what the next step is going to be, because sometimes that can tell me, real obviously if this is set up to be really easy algebra or difficult algebra. If I just look at it for a second. So I want to make sure that this goes to some number. And if it does, then that means that both of these are going to diverge. Okay. All right. So the next step that I would do with my algebra is I'd multiply by the reciprocal of the denominator. So n over 1. And yeah, look how nice that is. So n times n is just n squared. And if this is n squared, I just compare the degrees. So yeah, this is going to be pretty easy with the way that I set it up. But I always want to kind of think about the next couple steps just to be certain. So let's let the algebra take over. So we, multiply by the reciprocal of the denominator. And then that becomes n squared, limit as n goes to infinity of n squared over n squared plus 1. And then since the degree in the top is the same as the degree in the bottom, it just becomes a comparison of the lead coefficients, which is 1 in both cases. So I just get 1. And since this goes to just some number, that means that limit comparison test tells me that both of these are either going to converge or diverge. And since this thing diverges by the p-series, this one is also going to diverge. So here's my statement that I say. I say that the series diverges by limit comparison test. And the reason why is because the series that I'm comparing it to, n equals 1 to infinity of 1 over n, diverges by the p-series test. So, I just want to make sure that both of those are represented there. Yeah, we'll just get through number 20, and then that'll be it for this video. All right, next one. So we claimed that this one was the geometric series test. So that's how I'd say it. So I just noticed that r is equal to -2, and the absolute value of r is equal to 2. And since this number is more than or equal to 1, this will diverge by the geometric series test. So therefore, the series diverges by the geometric series test. Okay. 19, we already did that. That was nth term. So let's write up a little declarative statement. The series diverges by the nth term test for divergence, but I can just write it as nth term test. 19, I said that one was ratio test. So ratio test, again, the way that it works is you use the original sequence, and then wherever there's an n, you put in n plus 1. So 9 to the n plus 1 over n plus 1 to the 5th. And then you make a fraction, and then the denominator is going to be the same sequence. So just 9 to the n over n to the 5. Put an absolute value around it, and take the limit as n goes to infinity. All right, let's see what happens with this thing. Well, first off, I can get rid of the absolute values because if I'm just using n values from 1 to infinity, no matter what n I plug into 9 to the power of n plus 1, it's going to be positive. Same thing with the n to the first. And then no matter what I plug in for n from 1 to infinity into n plus 1 to the fifth or n to the fifth, it's going to be positive. So that's the first thing I do, just so I don't confuse myself. I just think about it for a second. Does it make sense to get rid of the absolute value? If it does, I'm just going to get rid of it right off the bat. Okay, and then it's dividing by a fraction, so multiply by the reciprocal. So that's 9 to the n plus 1 over n plus 1 to the fifth times n to the fifth over 9 to the n. Then I'd probably like expand the exponents. So 9 to the n plus 1 is the same thing as saying 9 times 9 to the n. And then I get n plus 1 to the fifth times 9 to the n. And then the 9 to the n's, like, they'll divide out. So then I get limit as n goes to infinity of n to the fifth times 9 over n plus 1 to the fifth. All right, then how do I want to handle this one? So here's the deal. I know that the bottom part is going to, have a power of n on it. So, man, let's see here. I don't want to expand the n plus 1. I don't want to use L'Hopital's rule a bunch of times. So, all right, here's what I'm thinking. You can either expand this out and then just do like the comparison of the degrees, or you can use L'Hopital's rule. I mean, I already know that this is going to be a fifth degree polynomial here. So would AP care if I just say that's a fifth degree polynomial? I don't think that they would. So yeah, you know what? I'm sure that they'll be all right with this, but I'll get some clarity on it. But okay, so either way, you know that like this is going to have an n to the fifth on it, right? Like as the biggest term. And then this one, even if you like FOIL it out or whatever, it's going to have n to the fifth plus like some other stuff, going all the way down to 1. But I don't care about all that other stuff. I just care that the degree in the top and the degree in the bottom are 5, because then I just compare the lead coefficient. And that's what I'm going to assume that I can do. So if I do that, if the degree in the top and the bottom are the same, which this will be, you just compare the lead coefficient. So it's just going to be 9 over 1, which is just 9. And since 9 is greater than or equal to 1, and that means that this thing is going to, if it's just greater than 1, that means that this thing is going to diverge. So that means that therefore the series diverges by the ratio test. There we go. So ratio test for this one. 20. Oh, this one's just a P series. Why didn't I write that down? I probably even said, it's P series in the video. Didn't write down. So 1 over n to the 0.4. So since the P value in this case is equal to 0.4, this thing is going to diverge by the P series, because if it's a number that's between 1 and 0, including 1, it'll diverge. So therefore, the series diverges by the P series test. There we go. So there's number 20. Can we get through the next ones quick? Yeah, we can. All right. We'll do 21, 22 also. I really got to get home. All right. Well, let's see here. So root test. So it's a power of n. So here's how it works. I take the limit as n goes to infinity of, and then I take the sequence in there. So n over 2n plus 1 to the power of n. And then I take the absolute value of that and then take the nth root. And the purpose of this is to like get rid of that nth power. So the nth root does that. So I can just immediately rewrite this as the limit as n goes to infinity of the absolute value of n over 2n plus 1. Now for whatever n values that we plug in, both those numbers are going to be positive in the top and the bottom. So I can get rid of the absolute value. So I'll rewrite this as the limit as n goes to infinity of n over 2n plus 1. Now here's the deal. If the limit ends up being more than 1, this is going to diverge. If If it's less than 1, it's going to converge. And then if it's equal to 1, it's inconclusive. But you can see real quickly what's going to happen here. This is a rational function. So the degree in the top and the first, and then the degree in the bottom, which is also 1. Since it's the same, we just compare the coefficients. So that's going to be 1/2. And since that number is less than 1, that means that this thing is going to converge. So I'll write out my little declarative statement here. Therefore, the series converges by the root test. Okay. And then 22, this is geometric series. We showed algebraically that it just becomes a geometric series pretty easily, and then we just compare the common ratios. So if r is equal to -1/3, then the absolute value of r is equal to 1/3, and that number is less than 1, and that means that this converges. So therefore, this thing converges by the geometric series test. Oh, well, let's write in the format that we have. Therefore, the series converges by the geometric series test. There we go. All right. And then we'll do all this stuff in a second video. Yeah, so it looks like we just got 2 more videos to go because these ones go pretty quick, the absolute, conditional, and divergence thing. Okay, that's it for this one. I hope you found it helpful. If not, just go seek out your math teacher. I'm Mr. Cook. If you need some help, please come by and see me. I'm always here to help you out. I'm available in the morning and also after school. So just find me. I'll help you out. Okay. I hope you enjoyed the video, and I'll see you in the next one. Bye-bye.